Now, the first thing that we need to discuss when talking about rings is the strain that's associated with them. And of course, this is not something new to chemists. As a matter of fact, in 1885, a chemist by the name of Adolf von Baer had already started to think about the ramifications for a cyclic structure. Why? Well, because if you think about carbon that is sp3 hybridized, the bond angles are 109.5 degrees. That is the ideal bond angle. But as we know from geometry, when you have small rings, the bond angles are much less than 109.5 degrees. And so what Baer said was he suggested that rings should be unstable based on their deviation of the bond angle from that of the tetrahedron. So that 109.5 degrees. So the more the deviation from that 109, the more strain there would be and the more unstable the molecule. And he referred to this as angle strain. And today we still call it angle strain. Sometimes it's actually referred to as the Baer angle strain. So let's take a look at cyclopropane. And if we think about cyclopropane, again, going back to geometry in high school, we know that the angle is 60 degrees, or it should be 60 degrees. But we have a problem because we know that sp3 carbons don't have a bond angle of 60 degrees. So what is going on in terms of the orbital picture? Well, in fact, if we take a look at the orientation of the orbital overlap, we can draw, each carbon has two sp3 hybridized orbitals that are bonding to another carbon. And then, of course, they have two sp3 orbitals that are bonding to hydrogens that I'm going to omit. So here's the two sp3 orbitals of carbon that are going to be bonding to the other two carbons. So now I'm going to draw the carbon on the top and its overlap of its sp3 to create that sigma bond. Now notice the overlap of the two sigma bonds is not linear, so this is not ideal, and that's going to weaken the bond itself. Remember, molecular orbitals form from symmetry, and they form from the overlap, and if that overlap is not head-on, that bond weakens, right? And of course, that carbon also has another sp3 hybridized orbital that's going to bond to the third carbon, and so I'm going to draw its two sp3 hybridized orbitals, and this is what you see in terms of orbital overlap. And we can actually measure the angle of the orbits, right? And we see that that angle, or orbitals, and we see that that angle is 104 degrees. So that is what we refer to as the interorbital angle. So yes, the visual angle is 60 degrees, but the interorbital angle is 104 degrees. Now, what that means is that the orbitals aren't deviating so much from that 109.5 degrees, but they are deviating, and the overlap of the orbitals becomes not ideal, let's say, and the bond actually becomes weaker. And we're going to see how we play that out in just a little bit. So that's the angle strain that's associated with cyclopropane. But there's also other strain that we've taken a look at in terms of thinking about conformations. And so if we draw out the structure of cyclopropane where that solid carbon-carbon bond is coming out at us, and then we have the hydrogens that are coming out of the board, and then we have the third carbon that's actually going behind us, and of course its two hydrogens are going even further behind us. And again, your model kit is ideal for looking at this type of structure. We see that all of the carbon-hydrogen bonds are eclipsed, right? If you think about looking, drawing a Newman projection, down a carbon-carbon bond. You see that the hydrogens are eclipsed to one another. And we saw, in terms of thinking about conformational analysis, we saw that eclipsed bonds have their own type of strain, which we called torsional strain. And so in this cyclopropane structure, we actually have two types of strain, angle strain and torsional strain. Now, how can we estimate how much angle strain we have and how much torsional strain we have? Well, the easiest way to think about it is, first and foremost, we have to have kind of a foundation to start with. How much total strain do we have? And the easiest way to figure that out is by comparing a carbon-carbon single bond of a straight chain alkane with that of the cyclopropane. So here I have butane, and if I analyze the bond energy, how much energy it requires to break that carbon-carbon bond, I see that it's about 88 kilocalories per mole. So for every linear, we say that for every linear alkane chain, the bond energy of a carbon-carbon bond ranges from between 80 and 90 kilocalories per mole. So butane's is 88 kilocalories per mole. Now, when we look at the bond energy to break the carbon-carbon single bond, that sigma bond of cyclopropane, we see that it's much lower. It's 65 kilocalories per mole. So it requires less energy to break that bond. And therefore, that's coming from the strain, the total strain associated with that molecule. And so we can simply say that the total strain is 88 kilocalories minus 65, which we get 23 kilocalories per mole. So that is the total strain. Now the question is, well, how much of that comes from angle strain and how much comes from torsional strain? Well, we can get a good idea of how much comes from the torsional strain by simply going back and reviewing what happens when a molecule like ethane rotates about its sigma bond. And we saw that when you rotate 60 degrees from a staggered conformation, you then get an eclipsed conformation, right? So this is the eclipse conformation. And we can observe that the eclipse conformation happens to be 3 kilocalories roughly per mole higher in energy than the staggered conformation. And that is all due to torsional strain from the eclipsed bonds. Now, if we think about it, there are 3 total carbon-hydrogen eclipsed bonds, right? So look at the molecule, understand there's 3 in ethane, 3 carbon-hydrogen eclipsed bonds. So if we take the 3 kilocalories per mole and we divide it by the 3 carbon-hydrogen bonds, then we get a torsional strain that is about 1 kilocalorie per mole per eclipsed carbon-hydrogen bond. Makes sense? So we can then take a look at how many eclipsed carbon-hydrogen bonds does cyclopropane have. And as we go around, we actually see that there are 6 eclipsed carbon-hydrogen bonds. Now it happens because the angle strain, the shape of the carbon hydrogen and the distance between the 2 carbon-hydrogen bonds is actually a little bit further apart. So it's predicted that it's going to be less than that of a normal ethane, but we can actually figure out at least the maximum amount of energy from that torsional strain. So we say that there's a maximum of 6 kilocalories per mole of torsional strain. Now, what does that mean? Well, if we go back to that 23 kilocalories per mole, which was our total strain on the molecule, and we subtract the 6 kilocalories per mole based on the maximum torsional strain, then we get roughly 17 kilocalories per mole of angle strain. And of course, this is we can analyze all of the cycloalkanes this way. Um, and we're going to kind of go through though and see how um, as you get larger in rings, there is a deviation. Cyclopropane's pretty easy to analyze. Why? Because it's planar. There is no deviation from planarity. However, once we get into cyclobutane, we're going to see, well, there's some slight deviation. So let's take a look at the structure of cyclobutane. I'm drawing that lower carbon kind of coming out at me. I drew a little wedge there. And if we assume that cyclobutane is planar, then we would have a very similar situation to that of the cyclopropane. And in all, there would be a total of 8 carbon-hydrogen eclipsed bonds. So we know that the torsional strain from that would be 8 kilocalories per mole. The problem in terms of analyzing the energy or the angle strain of cyclobutane is that now that we've added one more carbon, we actually give a little flexibility to that ring, and such that cyclobutane puckers, right? It actually twists out of the plane of the board. Now, how does it do that? Well, essentially, I'm going to push one of the carbons down, and so now I get this. It's almost like a boat that has no bottom, right? And I'm putting it upside down, basically. So there's this little pucker, and that's what we call it, a pucker. Now, when we think about the orientation of the hydrogens relative to one another, if I sight down this carbon-carbon bond here, I actually see, and it's kind of hard to visualize, so again, this is where your model kits really will help you out. Take a moment, pause the video, construct cyclobutane with your model kits, and you can really see what I'm talking about. When the ring puckers, as you look down that carbon-carbon bond, you can draw a Newman projection, and you see that now the hydrogens are staggered. So they aren't all eclipsed, and therefore we're actually minimizing torsional strain by puckering that geometry. Now, cyclobutane, like I said at the top, has a bond angle of 90 degrees, so it's going to have some angle strain associated with it. It still has that angle strain associated with it. We're just not quite sure how much angle strain there really is, because not only can we account for all of the torsional strain, since this distortion makes some of the hydrogens, not all of the hydrogens, but some of the hydrogens staggered to one another to minimize that strain. So number one, we know that it's going to have less angle strain than cyclopropane, because now instead of a 60-degree bond angle, there's a 90-degree bond angle, so there's better overlap of the sp3 orbitals. But on top of that, we're seeing an alleviation of the torsional strain that's associated with it. Keeping in mind, the carbon I'm looking down is the blue one, and of course the red carbon is hidden from me, it's behind me. And so that's how I draw the Newman projection of that particular structure, right? Now the cool thing about this ability to pucker is, because it's flexible, we can think about the ability of cyclobutane to pucker one of two ways. And so if I drew that puckered molecule again, showing one of the carbon-carbon bonds coming out at me, one going behind me, I can draw that type of structure. So hopefully you can visualize in that 2D picture what I'm actually representing in 3 dimensions. So now I can go from one, and I can actually interconvert into another, where the carbon on the left-hand side is now kind of coming down and the carbon on the right-hand side is going up. And that interconversion process actually requires energy, because now to go from one to the other, I actually have to um, cause eclipse bonds to occur. We can actually measure that energy of that interconversion, and we see that that energy is 1.4 kilocalories per mole of energy. So it's a very small amount of energy, but energy nonetheless. That, if we cooled this down enough, well, we'd have to cool it way down to actually capture one particular conformation. So that's cyclobutane. We see that, because you've added one more carbon, it allows the ring to actually pucker to alleviate some of the torsional strain that's associated with it. Not so much the angle strain, though. All right, so let's look at cyclopentane. Now, cyclopentane, if we were to draw it planar, again, going back to geometry, we see that the bond angle of that cyclopropane. I'm going to give you a little bit of time to think about what that bond angle is. See if you can remember what that bond angle is. Everybody tends to forget that of cyclopentane rings. But we're assuming that there's hydrogens all around, and all of those hydrogens are eclipsed to one another. So that's 10 carbon-hydrogen eclipse bonds, which is 10 kilocalories per mole of potential torsional strain. Potential torsional strain. But have you guessed what that bond angle is? It's 108 degrees. Now, 108 degrees is very little deviation from that 109.5. So that's the bond angle, 108, and therefore you're going to have, we expect to see fairly good overlap of the sp3 hybridized orbitals to form that sigma bond. So there's very little angle strain. However, because of all of the, we're actually increasing the torsional strain if the cyclopentane happens to be planar, and so because of that, it's going to distort, and it can distort into one of two forms. The first one I'm going to show you looks like this, where essentially 4 carbons are in the plane, the same plane as one another, and one carbon is coming either out at you, or you can think about it going down. And if you look at the the shape of this, it actually looks like an envelope, right? Where you can think about the carbon coming up as the flap of the envelope. So that's one conformation that cyclopentane undergoes, and of course it's minimizing energy in this process. Can it take on a planar geometry? It can, but that maximizes torsional strain. So to minimize torsional strain, one carbon can come up and it forms what's called an envelope. Another way that we can minimize torsional strain is if we have essentially 2 carbons coming up. So now basically none of the carbons are in the plane. We call this a twist conformation. So this minimizes torsional strain even further, such that you have very little eclipse bonds that are associated with cyclopentane. So this happens to be the lowest energy conformation, the twist does. Again, model kits are ideal for looking at this type of situation. The last ring that we're going to take a look at is cyclohexane. So cyclohexane, I'm drawing like this, where if it's again planar, and I have the 2 carbons coming out at me. We know that the bond angle of cyclohexane, I hope you remember, is 120 degrees. So now we have a situation where the bond angle is actually greater than 109.5 degrees. Again, if it's planar, we have a lot more carbon-hydrogen bonds. As a matter of fact, we have 12 carbon-hydrogen bonds that would be eclipsed, and so that's 12 kilocalories per mole of torsional strain. So we have angle strain because we're again deviating from 109.5, and we have torsional strain because we have 12 carbon hydrogen eclipsed bonds. Now it happens that both of these strains can be alleviated greatly by distorting that planarity, right? So cyclohexane is not planar. What does it look like? Well, again, I'm drawing this ring again, and what I want you to think about is we're going to deviate essentially by taking the carbon on the left and pulling it up, and then the carbon on the right, far right, pulling it down. What happens when you do that? Well, the structure looks something like this, right? So I've pulled up the carbon on the left and I've pushed down the carbon on the right. The four carbons kind of in the middle are still in the same plane as one another, but I get a geometry that looks something like this. And this is what we refer to as the chair conformation, right? The carbon that gets pulled up happens to be the back of the chair. The carbon that gets pushed down becomes the foot of the chair. And so this is what we call a chair conformation. Now, interestingly enough, if you think about the Newman projection of this, we're going to see how, what that looks like. Because again, your model kits are great in terms of visualizing what this particular structure looks like. And what happens when you do that, the bond angles actually become 111 degrees. So you decrease that 120 degrees to 111, and there is no torsional strain. How do I know that? Well, let's look down the axis, the carbon-carbon axis of the two carbons kind of simultaneously, and we can draw a Newman projection of it, and it looks like this, where all of the hydrogens are staggered from one another. So there are no eclipsed bonds when we distort that planar cyclohexane, which is a pretty cool thing. And it becomes, and cyclohexane becomes extremely stable, much more stable than Baer ever predicted. He predicted there'd be a lot of angle strain. And in fact, there's hardly any angle strain whatsoever. Now, because of this, we see cyclohexane rings popping up all over organic chemistry. And so we need to be able to draw this cyclohexane. So I'm going to try to help you out as much as I can, but again, practice, practice, practice. Practice makes perfect, okay? So how do we draw this cyclohexane in a kind of a consistent manner? Well, the first thing that you need to kind of recognize is that opposite bonds in the ring are parallel to one another. So if I drew that structure again, right, with the chair conformation, the left is the back and the right carbon is the foot, I see that there are parallel lines. So I see the horizontal lines are parallel and offset from one another, right? I'm going to draw it again. Right? So I see that the bonds in red are also parallel, and of course we have another set of parallel bonds right here. So when you're drawing that ring, you can think about drawing those parallel bonds, and it makes it a lot easier. Now, the other thing that we tend to do is we tend to tip the ring a little bit because it makes the whole structure easier to draw when you consider the substituents that are coming off of it. So what am I going to do? What do I mean by tipping? So I'm going to take this and I'm simply going to tilt it a little bit. I'm going to tilt the whole structure down. I'm not pushing one carbon back down and the other carbon up. I'm tilting the whole thing. And what I get from this is now the parallel lines that are running horizontal are actually going to be slanted up a little bit, right? So you see that I still have the carbon on the left that's pointing up. I still have the carbon on the right pointing down. But my parallel lines that were horizontal in the original structure are not horizontal anymore. Now, why do I do something like that? It actually is very easy to understand why. And that has to do with the position of the hydrogens on cyclohexane. So cyclohexane has 12 hydrogens on it. And the orientation of those hydrogens becomes very important. So when I tip it, what happens is on each carbon, one of the hydrogens is either pointing straight up or straight down. It's almost like, the hydrogens are going to be the base of my structure. And so they're completely vertical in the vertical direction. It makes it much easier to draw than having to draw all 12 hydrogens at various angles. And it makes it easier to kind of keep track of. So these hydrogens we call axial hydrogens, and there happens to be 6 axial hydrogens. So notice on the carbon on the far right-hand side, the bottom carbon on the right-hand side, the point of that carbon, that angle is, I like to think of it as coming down. So the axial hydrogen is also pointing down. Also notice, I've given the structure a little bit of depth because on one of the carbon-hydrogen bonds, in 3 dimensions, one's actually going to be behind a carbon-carbon bond when viewing it. And so you see that I've broken that carbon-hydrogen bond in the process. So I give it some 3-dimensionality. Now this takes practice, right? Trying to visualize that 3 dimensions on a 2-dimensional piece of paper is sometimes quite challenging. So practice drawing your structures. And it'll make things a lot easier for you to understand what's going on and for me to grade. All right, so we've accounted for 6 hydrogens. I said there are 12 hydrogens. Where are the other 6? Well, they are equatorial around kind of around the equator of the ring itself, right? And they happen to be parallel to adjacent carbon-carbon bonds. Drawing the equatorial hydrogens is probably the most challenging part of drawing cyclohexane, the cyclohexane with all of the hydrogens associated with it. So I'm going to take it one step at a time. I'm going to show you the orientation of the hydrogens. So I'm going to start with the carbon on the bottom right. And I see there's a hydrogen that is equatorial and it's coming up, right? If you remember, the axial hydrogen is coming down, the equatorial is coming up, but it's coming out at us as well. And there's, on the opposite side, a hydrogen, and it's down because there's an axial hydrogen pointing up, so it goes down. And those 2 hydrogens, their bonds, are parallel to the adjacent carbon-carbon bonds. So you see that parallelism? Now, I have another set that looks like this, that are parallel to the other, another set of adjacent carbon-carbon bonds. And then lastly, and this is probably the most difficult one, is the hydrogen that's coming out and the hydrogen that's going behind. Again, they run parallel to the adjacent carbon-carbon bonds. So hopefully that makes it a little bit easier for you to, see how the orientation of the equatorial hydrogens comes into play. And so now we can put all 6 of them together and it looks something like this. These are all equatorial hydrogens. They're all equatorial. So they're all kind of coming out away from the ring itself. That's important to understand, okay? Now, we can put everything together. We have our axial hydrogens, right? The ones that are in the axial position. They're vertical to the ring, and then we have our equatorial hydrogens. And so, if I take the structure on the on the left and I basically superimpose it onto the structure on the right, I get this. And that is the complete structure of cyclohexane with all of its hydrogens. And this simply shows the hydrogens in blue are axial, right? Notice there are 3 that are going down and there are 3 that are coming up. The hydrogens in red are equatorial. Also notice very closely that there are 3 pointing up and 3 pointing down. This is another thing that we need to be aware of in terms of, what bonds are above the plane of the cyclohexane ring and what bonds are below the plane of the cyclohexane ring. And this can be a little bit difficult to see initially. So I'm going to simply draw another structure showing all of the hydrogens above and all of the hydrogens below. So if I draw all the hydrogens above, there's the equatorial, axial, equatorial, axial, equatorial, axial, right? All of those hydrogens are above the plane of the board. We say they're up. They're the up hydrogens. And these are the ones that are in green. So now I can draw all the down hydrogens, and it looks something like this. And so I've drawn all of the down hydrogens in orange. So hopefully, with practice you can see the proper orientation of those hydrogens. Now the last thing that I want to talk about in this video deals with ring flipping. So we saw that cyclobutane can undergo this conformational change. Cyclohexane can also undergo a conformational change. And again, this takes quite a bit of practice to kind of visualize what's going on. But what we can do is we can number all of the carbons. So I start 1, 2, 3, 4, 5, 6. I've numbered all the carbons. What am I going to do? Well, what happens in a conformational change, the carbon number 4 goes down and the carbon number 1 goes up. And in essence, everything that's pointing up is going to go down and everything that's pointing down is now going to go up, right? So I can draw another conformation that looks like this, where notice the farthest carbon on the right is carbon number 1, and I've just pushed it up. The farthest carbon on the left happens to be carbon number 4, but now it's down. So if you follow, carbon 1 is now up, carbon 2, which was up, is now down, carbon 3, which was down, is now up, carbon 4, which was up, is now down. Carbon 5, it was down, now it's up, and carbon 6 was up, and now it's down. But keeping track of where everything is very important, especially when we have substituents on the ring. Now the other thing that's important is to recognize where the hydrogens go. So I'm going to draw that conformation and I'm going to put all of the hydrogens in. Right? So this is the structure with all the hydrogens. Now I'm going to highlight this particular equatorial hydrogen and see what happens when I undergo my ring flip. So when that carbon 1 flips up, the hydrogen's still on there, but what happens to it? Well, it goes up and becomes equatorial. So notice it's up, it's above the plane of my cyclohexane in the equatorial position in the original conformation. When it undergoes a ring flip, it then becomes axial. And so all of the equatorial hydrogens become axial hydrogens. So notice on C6, the hydrogen, the equatorial hydrogen pointing down now is still pointing down, but it's axial. On C5, it's pointing up, right? But now it's axial. C4, it's pointing down, axial. C3 pointing up, axial. C2 pointing down, axial. So they're all still on the same plane of the board, but now they're going from an axial position to an equatorial position. And of course, if that's occurring, then you see that all of the axial hydrogens initially become equatorial. right? So there's C1, C2, C3, equatorial. C4 is now equatorial, which it was axial. C5 is equatorial, right? Again, pointing down. And lastly, C6, which was axial, is now equatorial and pointing up, okay? Again, this is going to become very important when we think about what happens when a substituent is on the ring. It's going to move. It's going to go from equatorial to axial, to equatorial to axial. And this is an equilibrium process, and we're going to see what happens when you have substituents on in those positions, how the equilibrium changes.